Well, welcome back, folks, to another exciting chemistry video. Today, we are going to wrap up Unit 7 and finish our conversations on equilibrium. But today, we're going to be focusing on solubility equilibria. So what we're really focusing on are those salts that we've previously described as insoluble. The reality is that they're only slightly soluble and thus creating an equilibrium condition when we dissolve them in water. We're not only going to look at that, but we are also going to look at how we calculate molar solubility. That is, what is the maximum amount of solute that can dissolve in these equilibrium systems. And we'll also look at ways to apply things like Le Chatelier's principle in order to get more of our solute to dissolve or less of our solute to dissolve. So, without further ado, let's get going. Hey, make sure you like, comment, and subscribe as well. Do it now. Do it now. So today we're going to be able to analyze salts and understand that the dissolution of a salt is a reversible process where KSP is the solubility product constant. Calculate for molar solubility of a salt based on the KSP in the equilibrium expression for the dissolution of a salt. Explain how solubility is reduced in the presence of a common ion of the salt. Explain how this changes solubility based on Le Chatelier's principle. Explain how certain ions of weak acids and bases are reactive when acids and bases are added to the solution. And describe changes and shifts in equilibrium based on the addition of acids and bases to salts of ions of weak acids and bases. So this is definitely a little bit more complex than probably some of the labs that we've done previously. So it would be very beneficial to just kind of take things slow, make sure you ask questions, because the lab, there's really three parts that you're going to go through in the lab. First one is very simple. You're just going to be solving for the molar solubility of different salts in solution. That's a very simple calculation that you can perform. Secondly, we're going to be looking at what's called the Common-Lon Effect, which basically describes how when we put salts and dissolve them into solutions with common ions, or we add common ions, how that decreases or increases the molar solubility based on what type of solution we put them in. And it's kind of the same concept when we look at weak acids and weak bases. We know that they don't completely dissociate, so when we put them into a solution where they can kind of recombine to form weak acids and weak bases, we can actually increase the molar solubility of some of those salts. So let's go ahead and dive in and get started and see where we end up. So first, let's talk a little bit about solubility equilibria. So if you remember, you probably at one point in time in a chemistry class got a solubility chart, and that solubility chart basically told you these ions are soluble and these ions are insoluble. Well, it's not exactly true. Most ions and most salts that we describe as insoluble are really actually slightly soluble, meaning that only a certain percentage of them actually go through and dissociate when you put them into solution. So we would describe these as slightly soluble, and these actually form equilibrium concentrations. Most soluble salts have a K value that is greater than 1, which makes sense because that means that most of the salt dissociates into its ions, NaCl, NaNO3. Most ions that have sodium and potassium that start with those are 100% soluble, in addition to ones that have NO3 as their anion are going to be always completely soluble, but not all of them do. So since this is equilibria, we can write an expression for K. And this particular K, because we've talked about Ka and Kb for weak acids and bases, particularly this is called KSP, which is the solubility product constant. So it's the same basic concept here. We do need to remember that there are no solids. So in this case, we start off with a solid. If you look on the right here, we're going to start off with our solid salt, and it dissociates into its ions, which are aqueous in solution. Remember, we don't include solids in our equilibrium expression. So our KSP value is essentially going to be the concentration of our products to whatever power they dissociate into, or however many ions they dissociate into, rather. So for example, AgCl dissociates into Ag plus and Cl minus. So my KSP, my solubility product constant, is going to be equal to the concentration of Ag plus times the concentration of Cl minus. Keep in mind that if it dissociates into more than one ion, for example, MgF2, you have two F minus ions that are produced from that dissociation, that you need to take the concentration of F minus and take it to the power of 2, just like we've done with other equilibrium expressions. Now, as we go through and we solve for the values for these, as we determine something that's called the molar solubility, the value for X that we've done in other Rice tables Sometimes you'll see that as S, and S just stands for the molar solubility. Basically, that is the concentration of dissolved salt ions. So if I'm asking for the molar solubility, you're just simply going to solve for X. If I want to know how many ions, or the concentration of ions of each of my product, I'm going to plug that back in and solve for the concentration of that. You'll see that when we go through and we look at a practice problem. But I want you to look at the parallels between what we have done with equilibrium expressions previously and how that applies to the solubility product constant, because there are lots of similarities as we go through and complete these types of problems. So the KSP for Ag2CO3 is 8.10 times 10 to the negative 12th. It's asking you to determine the molar solubility of Ag2CO3. So as we go through and do this, the very first step always is to write our dissociation equation. That's going to give us a better idea of what our KSP is going to be and what we're going to set it equal to. We want to write our equilibrium expression correctly so that we can go through and solve for this problem. So when we write our dissociation equation, remember that they dissociate completely into its ions. So we're going to end up with 2 silver ions plus a carbonate ion. As we go through and complete this, we're going to make sure that we write out our Rice table. So this is our reaction. We also want to make sure that we write out our equilibrium equation correctly. So our KSP is equal to the concentration of silver ions squared times the concentration of our carbonate ions. Remember, that squared comes from the fact that Ag2CO3 dissociates into 2 silver ions. So as we go through and we write our ice table, we have no initial concentration of our aqueous ions of silver or our aqueous ions of carbonate. We don't really care that much about the concentration of our salt at the beginning because it is a solid, and remember that solids are not included in our equilibrium expressions. Remember that as that dissociates, we're going to gain 2 S ions. Just like what we've done previously, we'd put 2X there, but we use S because it's molar solubility. 2 S ions for Ag and S for CO3. Again, that's because Ag dissociates into 2 times the silver ions, and we get 1 carbonate ion from that. And then all we're going to do is take those values, 2S and S, and plug those into our equilibrium expression. We can set that equal to KSP, and then we can algebraically solve for S. So 2S squared is going to equal 4S squared times S is going to give us 4S cubed. And we set that equal to 8.10 times 10 to the negative 12th. And so our molar solubility, or S, is equal to 1.27 times 10 to the negative 4th. Now, if I want to go through and determine what the concentration of each ion is in solution, I'd plug those back into the equilibrium concentrations. So, for example, if I want to know how much carbonate ion I'm going to have, it's just S. So that's 1.27 times 10 to the negative 4th. If I want to know how much silver I'm going to get, I'm just going to multiply that value by 2. But that S value tells me how much concentration of Ag2CO3, what's the maximum amount that can dissociate and dissolve into Ag plus and CO3 minus ions. So that is our molar solubility. Now, the solubility of a salt is reduced when we place into a solution that already contains one of the ions of the salt. That is explained by Le Chatelier's principle. So imagine we add sodium carbonate to the equilibrium concentrations that are on the right here. Well, sodium is not going to have much of an impact on this, but carbonate is, because carbonate is found on the right side of the equation. So imagine we add more carbonate to the right side of the equation. Well, Le Chatelier's principle states that that is going to shift equilibrium to the left side of the equation. What that means is that the molar solubility is going to decrease as a result of adding sodium carbonate, because adding sodium carbonate increases the amount of carbonate. So if we add more product, Le Chatelier's principle says we're going to shift equilibrium to the left side of the equation. If we shift more to the left side, we end up with more solid, which means that less of it is going to dissociate into its ions. So you want to make sure you watch out for that as we go through and complete the lab, because one of the parts of the lab, is going to be looking for what types of ions decrease the amount of salt that can dissolve in the solution. So just keep an eye out for that. So let's take a look here. The molar solubility of lead 2 chloride is 1.62 times 10 to the negative 2nd molarity. The KSP for this is 1.7 times 10 to the negative 5th. Determine the molar solubility of lead 2 chloride in a 1.0 molarity NaCl solution. So again, just like before, what we need to do is we need to go ahead and write out our dissociation equation, which we've gone through and done here. PbCl2 gives me a lead ion plus 2 chloride ions. Let's go ahead and write our KSP expression for that. So KSP equals the concentration of lead times the concentration of chlorine squared. Now this is going to look a little bit different because we want to know the molar solubility of lead 2 chloride in a 0.10 molar NaCl solution. So this is going to look a little bit different because we already have 0.10 molar chlorine in the solution. So that's going to play a role in our calculations. You can see here with our initial values here, we have an initial value of 0 molarity for Pb. However, chlorine is going to have an initial value of 0.10 molar. That's because NaCl is going to dissociate into 0.10 molar Na ions and 0.10 molar Cl ions. So we're actually going to start with that as our initial. And just like what we've done before, our change, we're going to add S for our lead ions, and we're going to add 2S for our chlorine ions because PbCl2 will dissociate into 1 lead ion per 1 PbCl2 and 2 chlorine ions per 1 PbCl2. So we end up with these values. So from this point, now that we have these values, we can plug this into our equilibrium expression where our KSP is equal to the concentration of Pb at equilibrium times the concentration of Cl at equilibrium squared. Now we're going to do a little trick with this, and I've talked a little bit about this before, that if the KSP value is less than 1 times 10 to the negative third, we can actually eliminate anything that we add to an expression because that value is going to be very, very small, and it's going to have a very little impact on our actual value for S. So if we can assume that S is going to have a very small value, we can actually eliminate that plus 2S on the right-hand side of that equation, making this a lot simpler, simply because we won't have to use the quadratic formula to go through and solve for that. Now, you could go through and complete that and solve for the quadratic formula, but it's going to be pretty messy as you go through and solve for that. But if we assume a small value for that, what we end up doing is we end up squaring 0.10 molar, divide that on both sides, and what we get is basically 0.0000162 molar, or 1.7 times 10 to the negative fifth is our molar solubility. Now notice the difference between that and what we had originally. Our molar solubility of lead 2 chloride is 1.62 times 10 to the negative second molarity. When we have it in a 0.1 molar solution of NaCl, it decreases significantly to 1.7 times 10 to the negative fifth. So we can see that much less of the lead 2 chloride is going to dissociate in a solution of NaCl when compared to just a regular solution with water. And that's what I want you to be able to see here. All right, this is where this gets a little bit more confusing because changes in pH can shift equilibrium if one of the ions is from a weak acid or base, or it can form water. More basic simply implies that we add more OH minus to the solution. More acidic means we implies more H or H3O plus. Remember that weak acids and weak bases don't dissociate much, so they reform when you put them in acidic or basic solution, and that can actually remove ions from solutions. So for example, let's look at the top one on the right here. We have MgOH2 as a solid, which dissociates into magnesium and hydroxide solutions. So let's assume we add an acid. Let's assume we add HCl. Well, HCl is a strong acid, so it 100% completely dissociates into its ions. So is there anything of those ions, H plus or Cl minus, that would react with any of the products? And the answer is yes. The H plus in HCl is going to react with OH minus to form water. I don't know if you remember, but the Kw for water is 1 times 10 to the negative 14th, which means that very little H and OH minus would form when you're able to form water. So as a result, the H reacts with OH to form water. Well, what that does is that removes hydroxide ions from the solution. So as the concentration of OH minus goes down, that causes equilibrium to shift to the right, which means that the molar solubility of magnesium hydroxide is going to increase, again, because equilibrium shifts to the right. Let's look at the bottom one here. We have CaF2, which dissociates into calcium and 2 fluoride ions. Let's say we add an acid, HCl again. Is there anything in that, H plus or Cl minus, that would react with anything on the right-hand side here? And the answer is yes. F minus is an ion of a weak acid. Hydrofluoric acid is weak, meaning it does not dissociate very much into its ions. So the H and Cl is going to react with F minus to form HF, as F minus is the anion of a weak acid. The removal of F minus causes solubility to increase as equilibrium shifts to the right to make up for the fluoride ions that are lost. Just think about Le Chatelier's principle. As F minus concentration decreases, equilibrium shifts to the right to make up for that. That means that in an acidic solution, calcium fluoride's molar solubility is going to increase. So this is a bit tricky because you need to understand how these different ions are going to react when there is an acid present or when there is a base present. So it does get a little bit tricky. You'll see this as you go through and process information as you go through and complete the lab. So let's do one more practice problem and we'll call it a day for now. Lead oxalate, lead iodide, and lead sulfate are mostly insoluble with KSP values of 4.8 times 10 to the negative 10th, 1.7 times 10 to the negative 5th, and 2.53 times 10 to the negative 8th, respectively. What effect does adding an HCl, don't worry about the grammar there, I'll fix that later. What effect does adding a HCl, just one, have on their solubilities? Gotta work on my grammar sometimes. So let's go through step by step and keep in mind that adding HCl will add H plus and Cl minus ions to each of the solutions. So let's write out our dissociation equations for each of these and see if we can figure out what is going to happen as we go through and complete this. So PbC2O4 will dissociate into lead and oxalate ions, PbCl2 will add lead and chloride ions, and PbSO4 will add lead and sulfate ions to the solution. So let's think about this. Does adding HCl impact any chemical? So the very first one, C2O4 2- is an anion of a weak acid. We know our strong acids. Remember that your strong acids are HCl, HBr, HI, HNO3, H2SO4, and HClO4. C2O4 is not one of those. So as a result, it is an anion of a weak acid. If I look at PbCl2, adding HCl is going to add Cl-, and Cl- is a product. And remember that Pb2+ is a cation of a weak base. And so as a result of that, we're going to see a variety of shifts in equilibrium as a result of that. So let's take a look here. What's going to happen? Well, for the very first equation, adding that H+ is going to remove C2O4, which is going to cause a shift in equilibrium to the right. Remember that anions of weak acids are going to reform with H+ ions to form the acid, so therefore it's going to decrease the concentration of C2O4 ions and shift equilibrium to the right. Adding Cl is a product, and so as a result, we increase the number of chloride ions. That's going to shift equilibrium to the left as we increase the amount of chloride ion concentration. And Pb+2 is a cation of a weak base, so the addition of Cl removes Pb2+, and that's going to shift equilibrium to the right. So this can be a bit tricky, for sure. I'm not expecting perfection by any means on this, but just kind of keep in mind the concepts, and you just need to think about, do those ions have an impact on any one of the products that are present in the solution? So as you look at the first one, shift to the right is going to increase molar solubility. A shift to the left is going to decrease molar solubility, and a shift to the right will, again, increase molar solubility. So lots of different factors play a role in how this takes place. But again, ask questions, take your time, read through the directions, and again, ask me if you have any questions, because I know some of this can be a bit difficult for sure. Again, hopefully that explains some key concepts here. There are 3 parts of the lab that you're going to complete this week. Again, start early, ask questions, and if there's anything you need, please let me know. Take care, guys. Have a great day, and hopefully we will see you soon in the next video. We're getting close to the end, but we'll see you soon. Bye, everybody.